All right, we have something a little exciting here today. This is pretty different than anything I've really done before in terms of coding. It is just another, quantum video here, but the what I'm actually going to be doing here is pretty different. So what we're doing today is showing how I did the sort of MVP or minimum viable product of an integration with Qiskit runtime in OpenQAOA. So I say it's different because I don't usually modify existing software that much. I use it to do interesting things. And I also have never used Qiskit before on this channel. And that is, there is reasons for this that I won't go into now. But so OpenQAOA is a software that I've made 2 videos on now. And Qiskit Runtime had new tooling announced at the last week at the IBM Quantum Summit. Of course, I'll put the link in the description to the tutorial. There's actually a really great tutorial on the all the new tools that are in Qiskit Runtime for specifically error mitigation. And so that's what we're going to be looking at today, is how we can sort of integrate these two to do easy QAOA with fast Qiskit runtime sessions and fast Qiskit runtime error mitigation. So I'm not going to get into the sort of software of Qiskit runtime. There's resources that IBM has put out regarding it. If you look up on the Qiskit blogs or even on the latest summit announcements, I can put some of them I'll put some of them in the description. So you don't have to actually Google them. I'll just put them down there. So if you're curious, if you never used Qiskit Runtime before, you can check that stuff out in the description. So the first thing I'm going to say right off the bat is I put a message in the Discord being like, for OpenQAOA saying, hey, this is probably a good idea. Or I didn't say it like that, but I said, hey, it would be cool if OpenQAOA had these techniques, because the error mitigation, the new techniques of error mitigation in Qiskit Runtime are really easy to use. They don't require any advanced knowledge or anything like that. So it'd be great to sort of integrate this together. And I think the response was positive. Obviously, it takes time to allocate manpower and whatnot. So no rush on that. There's no rush on that. But I just wanted to show sort of a minimum viable, like, as an incentive, what can be done when you sort of do this integration, and sort of show how I think it can integrate. I'm not 100% sure if this is the best way to integrate it at all, but this is sort of my stab at it. I'm debating whether or not to make this code public. I actually did it all locally. I didn't even make a fork of the repo. It is extremely jank code. I would not advise using it, but I might, if there's interest, I can make it publicly available. The first thing I'm going to go through, so I'm going to talk a little bit about this process, right? Because I'm not an experienced software developer. Like, that's not my background. I haven't done a ton of software development. So, all these design decisions regarding software is something that I've been learning about a lot recently. I didn't take a class in that, well, actually I did, but I don't remember what I learned in that class. So I'm sort of trying to think about how to approach the integration of this Qiskit runtime tooling into OpenQAOA. So the first thing I need to do practically, right, because I know how to, from a design standpoint, I know exactly how this should work. But now from a coding standpoint, I have to actually figure out, how the hell do I implement this? So what I did first is figure out the actual workflow of OpenQAOA, because basically the way Qiskit Runtime works is you have to instantiate a session and then you pass your estimator calls inside of that session. The first thing I want to do is figure out where I want to initialize the session to minimize, wasted time on hardware or anything like that, and where and how this can all be integrated. So the first thing that needs to be done, as I said, is dive into the existing OpenQAOA software. And the way I did that is just by going through the code. I would This is another, I had some light suggestions last video. I'll have some more suggestions now. I looked at this figure 1, and if I scroll down here, figure 2, let me just make sure these are sharing. Yep. But this is not actually from programming integration standpoint. This does not tell me like what functions are being called. So this is where one of those things where you think about software design. The package is very object oriented. That comes with benefits and drawbacks. One of the benefits is that it's sort of right. There's an ease of use from the user perspective is good. Sometimes it can be hard to work with though, because you have this object that's getting passed around, or things are changing inside the object through a variety of different places. And so keeping track of that is hard, right? If you had a functional, right, you'd say, okay, I know what the input and output to every function is, so I know exactly where to zoom in instantly to address my changes from a programming perspective. But if the objects are getting passed around, it makes it a little challenging sometimes. I'm also not an excellent software engineer, so maybe if you're an excellent software engineer, you say, you're just bad, get good. But anyway, what I was going to say and recommend, perhaps, just an idea, I have a lot of ideas, is that this paper, I haven't really read this paper, I just saw it and it said this is like a great example, this automated error mitigation, is this right here. I've seen examples like these diagrams before. I don't know, I guess they're called a UML diagram. I don't know what a UML diagram is, but this sort of flow is very useful where you can see, so this is, these are classes that have, there's just information here. I'm just assuming, I haven't actually looked at the code, classes and attributes and what they do. And you can see pluses and minuses, like this sort of exact flow, right? Where I can see, okay, this goes to here. The experiment is the end goal. So we go here, we can go up from here, right? This is clear, represent dependency. So all of this gives a lot of insight into how the code goes through, right? So the first thing that I went through is saying, okay, when I call this basic workflow, compile and optimize, right? The optimize is what we want to change, but we also need to look at compile. So I'd actually go through and say, what functions are actually getting called here and how does it go through these processes? So now we're going to jump over to the code to actually show what I did. So this is sort of this is what I wrote down for myself. So we specify a device. We then compile it. The device is passed to the object, the QAOA object. In compile, it calls get QAOA backend, which then generates, for example, here we're talking about Qiskit, so it'll be a Qiskit runtime or a Qiskit backend, which itself inherits from a base backend, which has this expectation function that we're going to need to care about and override. We're going to want to override this because we're using now the estimator primitive instead of the sort of from counts or from get counts or whatever. Then optimize calls internal function called self.optimize this, which then calls the VQA, which is from this, is what is generated from the backend, basically dot expectation. So you can see why we're going to need that. So we need to, inside optimize, we want to put our session, we wanted to override the expectation using runtime, and then I'm just passing in options like, so Qiskit runtime has these options class, right, that you just pass in. So that is sort of like the simplest example. So the first thing we're going to do is create a new device. So if we go down here, we can see this is the devices.py. You have the IBM, the I think QCS is Rigetti, AWS, local, and now I added runtime. So there's a new runtime device here. If we actually go up to the code, you can see it's not a lot of code that I actually had to change here. It's going to be a lot more if you want to integrate it actually like properly, as you're going to shortly notice. This is very jank, but it does work, I will note. You can see, for example, I just specify a few things. One, to bypass some checks that we'll see later. I didn't want to deal with networking. I don't know how networking works. So I just wrote, it's always going to work is my assumption. So I just said, yes, it's connected, true. Everything's true. It's always going to work. The things that we need the information for are this device name. So this is going to be the actual hardware, right? So in my examples that we're going to be talking about, I used Perth, IBM_Perth. Then the service, which is the Qiskit runtime service, which is basically a little class that contains like your API access and all of that. And then we're going to also put in the options. And this options class has pretty much everything you would, care about. It has the shots, it has all sorts of stuff like that. Importantly, the error mitigation is also in there. It has the optimization level and stuff like that. So this is all we need, right? Because the interaction with Qiskit runtime is simple, right? You initialize your session, you have your estimator, you have your Hamiltonian, you're good to go. So we don't need, if we look and compare, for example, this is the Qiskit one. I wrote no documentation as well. You can see this is just check connection, check backend, check provider. All this stuff is not necessary because I'm just assuming it's going to work. So now we want to talk about the actual backend. So here we have this is what the function calls, right? Get QAOA backend. So what needs to change in this function is actually nothing. It's the exact same. However, we do have to actually add the options for Qiskit runtime here. So we have to do the proper imports. We can see I made a new Qiskit runtime backend that we'll talk about in a second. The device has to be here, and we have to have the mapping, right? We want to say the runtime device goes with the runtime backend. Same thing goes here. We want to say, okay, we have a new service and options that we can then put in down here. We could say, okay, those are only going to be relevant for Qiskit runtime. So we just have to add them in this function. So now let's talk about the backend. As I said, I made a new backend. We can see it inherits from this class here, not that one, QAOA base backend, which has a expectation method inside of it, which computes from the counts the cost. And so we're going to want to override this, but I didn't want to do too much work because, this is sort of the minimal example. So we're actually going to make our runtime backend inherit from the QAOA Qiskit QPU backend, because this has a lot of code in here. So this is now in the specific file for the Qiskit QPU backend. This has a lot of code in here that I don't really know what it does, and I don't want to rewrite it. QAOA circuit that generates a circuit. This is a nice parametric. There's a lot of stuff in here. I don't want to rewrite it. So I'm just going to inherit from this and get all of these methods in it. The only thing I'll note before we go down to the actual QAOA runtime backend is that we need some imports from runtime. All we're going to be taking here is the estimator because we need to generate the expectation value. Then from quantum info, we need a sparse polyop, which is how we're going to represent the Hamiltonian that we're passing to this estimator call. So now we can actually go look. As you can see, once again, it's not actually that much code, but it did take a little while. It only took me maybe 2 hours or something to write this all up, just because I had to figure out how to do all of this. So all the same things are imported. I just remove. You can see, once again, very jank because I'm just removing the type hints here for the devices. I don't want to deal with that, so I just remove it. The device gets passed to the QPU backend, but is irrelevant here because remember, this is actually why I put it in. This runtime device gets passed to the Qiskit QPU backend, which then checks like the network. But I don't want to deal with those tests, so I just default them to true. And then we have our device here. We have our estimator, which we initialize to none. And then we have our Qiskit Hamiltonian, right? Because we need to work in Qiskit native sort of terminology for Qiskit runtime. So we have to convert our circuit or our cost Hamiltonian to a Qiskit Hamiltonian. I don't know if this is actually like a robust way of doing it. I found that it seemed to work for my example. So basically, sparse polyop you can do from a list where you have a list of strings and coefficients. And so we have this. So first we have identity on all the qubits, and then we say, okay, for the terms at each of the qubit indices, we're going to have a ZZ, right? Because that's our edge measurement, basically, between the two nodes. That's the edge we're measuring. And then we, join the string together because it has to be a list because strings are not mutable, of course, in Python. And then we append the Hamiltonian coefficient and this new string Hamiltonian. Then we create this sparse polyop. Once again, I don't know if this is super robust to different kinds of Hamiltonians, or if there's X's in the Hamiltonian. You know, this is not super robust, is all I'm trying to say, probably. And then the expectation. This might be improvable. I'm not a super expert on the latest and greatest, you know, how to integrate runtime into your software, but the first thing we want to do is get our circuit. We want to remove our final measurements. I don't know if this is strictly necessary, but we're not measuring, like runtime handles the measurement for us and all the bases that we care about. So let's just remove anything potentially a problem. Now, if this is the first time we're calling expectation, we want to initialize our estimator primitive. Once again, I'm using the Qiskit runtime terminology. If you want to know more, check out the description. We initialize our session, right? So this is the context with which we're calling the estimator, and our options. If we already have a session, then we don't need to do this. We run our circuit and our Hamiltonian to get the result. We get our job result, and then we get the, I don't know if we even need to do the sum. I think it will like handle that for us, but we sum the results to make it a nice format, right? Because it's the sum of these expectation values. And so that's all we have to do for this backend. So what's left? Not much. We just have to go into the optimizer now and say, okay, we have a way to get the expectation using Qiskit runtime. Now we just need to initialize our session and pass this to runtime, to the primitive here. So we have in the optimizer, there's just one line I changed, which is to pass the device to the optimizer, because we need the device because that contains information about how we're going to initialize our session. And once again, there may be ways to, deal with this. Like you're passing the device for only one case, there's probably ways to improve this, is all I'm saying. And then in the training VQA, we can see a couple examples here. So what we're doing, the first thing we're doing is we're saying once it calls optimize, well, all we're going to do is we're going to ignore gradient-free optimizers. We're going to ignore the not gradient-free optimizers. I'm just doing this one specific example. So once again, this is not robust code. This is just the minimum. So we're going to say if it's a runtime device, if it's not, just do the normal process. But if it is, initialize your sessions. You do with session, and this is why we pass the device. We have the service and the device name here as our session. So we initialize the context, and then we pass the args we pass a session as an argument to our optimize this function. So then if I scroll up to the optimize this function, we can see this is where it actually calls the expectation. So the first thing, I have a few print statements here just for debugging purposes. There's one here and there's one here. You can see here we can say that if there is no session, then we can just get our expectation normally, because that's the non runtime case. But if there is, then we want to pass the session to our expectation, and that way if the first time that we create this estimator primitive, we're going to want to contextualize it with this session. I just add this because there's no measurement outcome, so there's no attribute there. And then that's pretty much it. That is all the code I changed in total. Maybe, let's see, this is probably most of it. So, this is what, 40 lines of code. So in total, less than 100 lines of code to get the minimum example working. Making it robust, I'm not denying, would take a lot of work. So now let's actually jump into it and say, well, does this work? Okay, well, let's see. So we're going to go over to now this Jupyter notebook. So the first thing we want to do is super basic max cut tests. That's all, we're not doing super exciting quantum right now. We're just doing the integration part. So what we have here is not only that, I'm trying to make it as friendly as possible. We have a 7 qubit graph that is the exact topology of the 7 qubit systems on IBM. So Perth, if you move this over, you'll see it's this exact I shape is the topology of the hardware. we generate our max cut from this graph and we get our problem. We have our solution, which is fine. And then we compare it. We're going to be, of course, comparing it to the default methods. So we're just going to use Cobala, and we have our state vector simulator local and our chasm simulator local. And so once again, I did this to ensure that I didn't break the existing code, right? That happens. So these changes don't break anything besides adding runtime is all I'm trying to say here. You can see, just for the sake of comparison, I'm initializing everything to the 0, 0 state for p equals 2. So that way it's a fair-ish comparison. You can see there's some nice print functions I'm doing because of the debugging, and you can see the results here. You can see the state vector goes nice and to like -4, and you can see the noise-free shot simulator goes to about -3. And so that's just basic OpenQAOA tooling. If you want to know more, check out my previous videos. So now we need to actually deal with runtime. And so this is where it's like you might want to integrate more of this into OpenQAOA. Like right now, a lot of it is exposed to the user. So we have our runtime from Qiskit IBM Runtime. We're importing the service and the options. So we initialize our service, which I have already saved on my computer with the API key. And then this is just a list of accessible backends. This is actually my old, there's like a program where if you're like affiliated with a university, you can get access to a few more systems. And so this is from my my university account is what this is from. So when I was in school, I created this and got access to this, and I guess I still have access to this. So that's what we're working with here. So then we're going to look at the simulator, and Perth is our backend of choice. I just did that because the queue times were basically the best. No, and it seemed like a good backend. I didn't test it with other ones. That's all. So the first thing we're going to be doing is this runtime simulator. So we're doing the resilience level, and the shots are how you access the two things we're going to be changing. The resilience level changes the level of error mitigation. For the estimator primitive, resilience level 0 has no effect. Resilience level 1 does T-Rex, which is twirling readout error mitigation. Level 2 does ZNE, zero noise extrapolation. And level 3 does PEC, probabilistic error cancellation. And that generally, those are sort of thought of as increasing in the quality of error mitigation, but increasing the cost as well. Now, I'm not sure if that's exactly true in every scenario, but that's sort of my impression. So the exact same code is used here. We just have to specify our device here as a runtime device now, with the name and the service and the options passed in. And then we run this and we can compare it. You can see it's not the exact same because I'm not using a seed on the runtime simulator. So this is going off to the cloud simulator, IBM Chasm simulator on the cloud. But you can see it converges to the same value, even though the exact trend isn't the same. I also don't know if Coppola is actually deterministic. So yeah, this is the trajectory here that it's going. And so you can see it's working exactly as we would expect. I mean, there's more shots, but converging to the same point. So now let's do the hardware. It's the exact same usage. We just specify different options. Same exact, we just create a device. I literally just copied this code and changed the name of the object. Then we do resilient. So we're going to compare 0, no mitigation, 1, which is sort of twirling readout, 2, ZNE, and 3, PEC. And once again, these are the exact same blocks, just with the names change. You can see some executions here, lots of executions, lots of executions. The one thing I'll note here, you can see runtime 3 is the PEC was having a rough go of it. PEC is my impression, once again, I don't know a ton about error mitigation. My impression is that obviously a lot of methods scale exponentially, but PEC can be very costly to do. It can give really good results, but it can be pretty expensive. And so with my limited access, right, this is just a little, tiny school account that I had. I was hitting sort of timeouts, like you'd say, oh, hey, you're trying to run too many jobs, you're running them too long. And so that is a cost there. The one thing I want to say is if I go to my account and look at the I can look at the history of jobs. What I'll say is that the resilience level in 0 and 1 took approximately, so if you go to your job view on the IBM Quantum website and you look at so you look at all your jobs, they'll have the ID, session ID, status, etc. If you look at the Qiskit runtime usage, the number of seconds there, the no resilience levels took about 8 seconds per expectation value calculation, because I'm running obviously multiple circuits. With T-Rex, resilience level 1 took about 9 seconds. With ZNE, resilience level 2 took about 13, well, 12 to 15 seconds really. And then with with the PEC, or resilience level 3, it was taking about 1 minute and 33 seconds per execution. I'm not sure though what the process is, because I would see 1 minute and 33 seconds, or plus or minus a little, for a bunch of estimator calls, and then it would suddenly spike to 16, 17 minutes. So I don't know. So PEC, right, like learns the noise and it mitigates it. So I don't know if it's like the noise suddenly spiked in difficulty of learning, but I think there's more work to be done for PEC here. But I didn't really have a huge amount of hardware access to sort of go and work on debugging this. So then we get the results here, and we plot them. We compare it to the state vector. So we can see here that this is the default hardware results here. We can see green is the runtime simulator. So this is the noiseless but with shot simulator. This is default hardware, right? Hardware is very noisy right now. So, you're not going to get as good results as simulator. That's just sort of the widely known, fact. The readout error mitigation here doesn't seem to be doing a ton. I don't know, variational algorithms are sort of hard to predict. But we can see here that this is the state vectors. Oh my, I just got I got a notification on my phone there, email, but it's a different ping than usual. And so what's going on here is we can see that with ZNE, we are able to reach the same quality results as a noiseless simulator, state vector simulator. So this beats, this ZNE on real hardware, 100% real hardware, beats a simulation, which is really cool. I often, don't know exactly what to expect when you run things on real hardware. There's a lot of limitations, but it's super cool that, obviously there's a lot of work. Well, it was a fair amount of work to integrate with the software, but a simple flick of the switch, right? Like, I know how ZNE works. You extrapolate by adding noise, but I can't implement that right now. I wouldn't know how to implement that right now in OpenQAOA or Qiskit or something like that. But with a simple flick of the switch, you can just, bam, instantly, at the cost of 5 extra seconds per expectation value, probably because it's has to run more to generate the things to extrapolate from. It gets super good results, which I think is really, that's just really cool to me. I saw this, I was like, this is amazing. So now we're going to look again. And this is just comparing the different error mitigation strategies. You can see PEC does the little normal amount, but it doesn't go further because, once again, as I said, I timed out. So yeah, I think this is really cool. So that's all I wanted to show, basically, is that this is how I did a minimum integration of Qiskit runtime with error mitigation into OpenQAOA. I think there's a lot of potential here. Look, if all the results were like this and they were pretty mediocre, I would say, whatever. But this is, I think, a compelling result. I don't know how it generalizes. Maybe I got super lucky. Maybe 7 qubits, it doesn't, get any, it scales terribly. I don't know. But I think this is really cool. And when I got this result, I was like really motivated then to like say, hey, I should sit down and make this video, because this is cool. Getting these results is really, I think I'm saying the same thing, I know, but it's cool, and I think there's a lot of potential here for error mitigation to pave a path, for quantum computing use cases, and we see that right now with this example. So yeah, I think that's it. That's basically sort of the minimum work required to integrate OpenQAOA with Qiskit runtime error mitigation. Maybe more software will use error mitigation and show how maybe it's the key to unlocking VQEs or something. I don't know. But yeah, that's pretty much it. Once again, I'll put the links to the papers I referenced in the description, and I'll put some information on Qiskit runtime in the description. And yeah, that's it for now.